Hello, Tensor friends. Here's something that was a lot of fun, but for me it was very challenging because it uses a lot of the tensor calculus, the syntax, uh, in balancing the indices around. The most I've done so far, and that's the reason I did it. This isn't all the books. This is not something I did. I'm not smart enough. Okay, this is the derivation of the Riemann curvature tensor using parallel transport. All right. So back in the day, Bernard Riemann envisioned that if he was walking on a surface of a sphere, holding, as an example, a javelin, and pointing it at the horizon, and he continued to walk, but holding it, pointing at the horizon as well as he could, got down to some point on this sphere. Then he walked sideways, holding it at the horizon, and then walk backwards to the origin of where he started. And if these two things were unequal in direction, then the manifold, the surface, was curved. If they were the same, the surface was flat. So this is how I read that he envisioned this, right? So what we're going to do is to take the directional derivative along the right path and then the left path, and then we're going to do something called the commutator, which is written as this: r comma l. So if r times l minus l times r is equal to 0, then the surface, the manifold, is flat. If it's not equal to 0, then the surface manifold is curved. All right, so we're going to jump right in here with the covariant derivative. Now, I'm going to leave a link to this in the description. I did a video on the covariant derivative of a contravariant vector component, right? And I'm writing my covariant derivative as a big D with the subscript. And this is telling me I'm taking the ith derivative with respect to the jth component of this vector component. Let me say that again. I'm taking the ith derivative with respect to the jth coordinate. And that gives me what you normally would think of as the directional derivative plus this added term, which accounts for the fact that the basis vectors may be changing in the space. And this you recognize is called the Christoffel, the symbol, the connection coefficient. So it connects this directional derivative to the fact that those basis vectors may be changing. And if it's curved, they will be changing. We're also going to use a covariant derivative of a covariant vector component. Also, I did a video on that also, and I'll put that in the link. So you notice here that it's written in the lower index for covariant. And what you get here then in between these two is a negative. Up here we have a positive, here we have a negative, but it's the same, the reasoning of what these two things are. And it explains why that's a negative in the other video. I don't want to go into it here because it's too lengthy, all right? So we're going to write our commutator as di comma dj of this contravariant vector component, right? So we're going to have this minus that times this. And we're going to take that inside and show the covariant derivative of this first. Then we take the covariant derivative of that. Then we do it again in the opposite order and subtract them. Okay? So let's get cracking. All right, so we've got our vector component, and we just did this upstairs. So we got the directional derivative you're used to seeing. We've got k, j, m of the Christoffel symbols, and now we have to rename this vector component as a m because we have to maintain these things called free indexes. So we've got j, k, and I are the free indexes. All right, we can't change those. Anything else that you see an upper and a lower is called a dummy index in tensor calculus. In relativity, it's called a summation index, okay? So when I take the derivative of this one index, the tensor, it winds up giving me a two index, the the tensor. And you see where the indexes are. They're in the contravariate position and the covariant position, just like this, right? So you got KJ, KJ. And I just made up P. It's just a tensor I made up. And the reason I'm doing this because I want to take that and put it in here and then take this derivative of this 2-index, the tensor. Okay? So here's what our PKJ looks like. And we know that because we just saw it above. So I'm going to put it in the equation like this. Now, this is different. You notice immediately. And here's the reason. Because this 2-index tensor has a contravariant component and a covariant component. So we have the directional derivative of it, but now we need to have two connections because we have two different types of indices. The first one being positive and the second one being negative. So this is for the contravariant connection and this is for the covariant connection. All right. Now look at these indices. We got IJK, so those are our free indexes, all right? We can't monkey with those. But over here, we do need to have a summation index because there's more than one term here. There could be many terms here. So we make up a new index. I did L, so we got LL here, and now we're going to have LL here too. And we keep our KIJ, KIJ. So for me, this was the beginning of the difficult part of understanding this. But I tell you, once you go through this, you will learn a lot about the syntax and how to keep them straight. All right, so we're going to take this guy here and put what the PKJ was, and here he is, right inside this. All right. So here's the first term, here's the second term, here's the third term. Now we're going to differentiate this, and you see that we're taking the differential of a differential, so that gives us a second order differential with respect to IJ. And here we have to use the product rule, so the derivative of this times that plus the derivative of this times that. All right, so here they are. The indices stayed the same. All right, so we got XI, XI. We got KJM. Yeah, there was no changing here. But here's something that's going to happen. We're going to take now the product of this with this term in the parentheses. And you already see a problem. We got a KK here. We can't do that. Because remember, KIJ can't be changed. They're free indexes. All right. So I've got to change the something here for the fact that this is going to be a summation index. So the way I do that is just change the index on the vector component and one index on the Christoffel, the symbol. So I have LL, all right? And when you multiply this one times this one, you have the same thing. You have to change this such that you got LL. Now here's another one. Well, I had to make up another index because I can't have these together. So I got MM here, all right? And then we go do this one, and it's exactly the same, the problem. You just have to go through each one of these and make sure you're maintaining your free indexes and that your summation indexes are in the upper and lower position and they don't contradict each other, okay? So you can see this is a double. Here's an L up here and an L up here and an M up here and an M. This is a double sum, all right? Now, so this is the derivative, the ith derivative of this, the first derivative we did, all right? Now we've got to do the same thing but backwards. We'd have to take the ith derivative and then take the jth derivative of it. Now here's a trick I learned from Professor Jim Fowler's YouTube channel called Tensor the Calculus. When you want to do this, all you have to do is use the formula and go through and change the J and the I. You just swap the J and the I. So that is so much easier than having to redo all this again. So I took this equation and carefully went through and changed all the I's to J's and the J's to I's. Now what we got to do is subtract these two things, okay? So we're going to subtract this one from this one. And we're going to jump over to the pad. What do you call that thing? The drawing the pad, and go through each one of these. So that'll be now. Okay, let's switch to the writing tablet so we can look at these in detail. Okay, so here's my first equation, my second equation. So I'm going to subtract this one from this one, okay? So let's look at each term. Here we have a second derivative of a vector component with respect to two coordinates. So the order of differentiation is not the same. So the partial with respect to j or partial with respect to I, it's the same thing, okay? So these two can drop. They're equal. Let's look at this one. We got the partial of a Christoffel symbol with respect to xi. Do you see any of those? Partial of the Christoffel? No. Okay, can't do anything with that one. What about this one? The partial of vector component with respect to xi. Okay, here's one. Now, this is important. Look at this. So we have an m in the upper and an m in the lower. But you say, well, that's not an m. Here we have an L in the upper and an L in the lower. Well, these are dummy indices. You can rename them to George if you want to. It doesn't matter. What you can't change are the free indexes. That's a free index and that's a free index. So if I change this to mm, then these two are equal. So this minus that is 0. Now let's look at this one. We got another one, v. We got an L in the upper, L in the lower. So we're looking for differentiation with respect to xj. Can we find one? xj. Here's one right here. All right, is it v? Yes, m in the upper and m in the lower. And the free indexes are the same, k and j, k and j. Oh, that's good. Get rid of these two. All right, let's look at this guy. We got two gammas and a vector component. Here's two gammas and a vector component. Let's see, we got the dummy index here is LL across. Here it's LL across. But I got a free index of J and a free index of I. And I can't do anything about those. Okay, let's look at this one. We got the partial of VK with respect to XL. But look at this. That's not a free index, all right? That's a dummy index. So look down here. I got the same thing. Look at that's out of the screen or something. That's so weird. Anyway, we got a LL here. All right. Now you say, oh, wait, this is IJ and this is JI. Well, Christoffel symbols are symmetric across these bottom indices. You can swap them and they're equal. All right. So I can get rid of this one and this one. So what we got left here, we got 1, 2, 3, 4, 5. We still got too many. So let's look at this one. We got a LL here and an MM here. We got a LL here and an MM here. Once again, it's IJ, JI. They're equal. So this minus a minus is a plus, right? So that goes away too. So we got 1, 2, 3, 4 left. And that's exactly how many we should have left. All right. So we can switch back now to our document. Okay, we're back from our drawing the pad. And when we did the cancellation, we were left with these four terms. So this is the commutator that we come up with respect to this vector component. And you notice we have that component in every term, so we can factor that out. And we can gather like with like, so this partial with this partial, and this product with this the product, and we get this term. Now, what's inside this parentheses is the Riemann Curvature Tensor, okay? It looks like this. It's a 4-index the tensor. And you say, well, why is this a 4-index the tensor? Well, you remember when we took the way up here, we took the derivative of a 1-index tensor, and we got a 2-index the tensor? Well, we took the derivative of it again, remember? So that gives us a 3-index the tensor. So inside this equation here, in here, it is a 3-index the tensor, but because you've got this vector component with the same letter, these contract. But standalone equation by itself, it's a 4-index tensor. I hope that makes sense. And this is the equation you use to determine in general relativity if the space you're working in is curved. Okay? So I thought that was a lot of fun. I learned a lot. I really did. And I would encourage anyone to go through this exercise. You're going to really learn how to manipulate these indices and understand the syntax of tensor calculus. All right, I'll see you later.